The last part I want to discuss is about some challenges and issues when it comes to threading. So the plan here is to show you, to give you more evidence about what I said since the very first lecture here. That is, when you want to do something fancy, more advanced, that gives you better performance, you need to pay a cost, and it gets more complicated. So I'm going to give you some hints about why it's more complicated and aspects that who designs a system that supports multi-thread processes need to think about. Let's start with the semantics of fork or exec. So this is the code we discussed already in a previous video. Okay, so we have the process running, calling fork, then we create two processes, they are copies, we check if the fork was successful, and if that is the case, we have the child process running exec to replace the memory and run a different program, and the parent process that is waiting for the child, and then printing that everything is done, and finally exiting. You can think about questions like this. Does fork duplicate only the calling thread or all the threads? Answer, it depends. So I'm not saying this because you need to know what is actually being done inside the fork. It depends on the implementation you have of it and the Unix system you're using. But the point I'm trying to make is that such a question arises now because we have multi-threaded processes. If each process had a single thread, we would not need to think about these kind of things. Okay. Similar questions can be made for the exec, although in practice the exec will replace everything, and since it replace everything with a different program, it will start with one thread. Usually it would be really strange to keep all the threads, since what the next program will do is potentially completely different from what the current one is doing. Another aspect to take into account is that of handling signals. Okay, so signals are used in Unix systems to send messages between threads and processes. When a process runs wait and asks the operating system to notify it when, for example, the child process has terminated, all these messages are handled by the kernel through signals. Now, if you have single-threaded processes and you send a signal to a process, it's pretty easy who you should contact. You, in this case, it's the operating system. It's easy to understand who the kernel should contact. The process, which is the thread, the single-threaded process. On the other hand, if a process has multiple threads, then you can imagine that you can have legit questions like this. Should I deliver the signal to a specific thread in the process? And if the answer is yes, how do I know which is the specific thread that should get the signal? Or should I notify all the threads of the process? And of course, which one of the two is the options to go might depend on the process you're running. So both options might be valid, and you might want, as an operating system, to provide functionality so that you can choose which one of the two. Okay, so what I'm trying to say here, simply put, is that all the handling of signals becomes way more complicated once you start having multi-threaded processes instead of single-threaded ones. And then you also need to take into account how you handle the cancellation of threads. Okay, so there are two ways in which you can go, basically. Okay, and you have the details here. Actually, in the next slide, you also have more details in the table about how it actually works. But simply put, you can either terminate the target thread immediately. So if thread A says kill thread B, then this will be done. But what you usually do is that you actually signal your intention. So if A wants to terminate B, A signals the intention of doing this to B, but it asks B to actually terminate itself as soon as possible. Okay, and this is called deferred cancellation. The idea here is that you want B to stop, but you can wait a bit until B is done completing whatever it is doing. So if B is operating on some file, okay, and you want to stop B, if you kill it immediately, then it might die without storing the file to disk, for example. And as we will discuss later on, since there might be buffering in the main memory, terminating the program before it's done in an abruptly way, then might create problems. So you do this deferred cancellation and you say, I would like you to stop. And the target thread in this case will periodically check whether it got a signal that it should stop, and in that case close whatever it is doing and then terminate. Okay, and you have this function here, pthread test cancel for this.